So in the last couple of lectures, we've been discussing about work done by variable force. And last time we understood the formula for work done by a spring. And we also understood the work kinetic energy theorem, the relationship between work done by the net force or net work done and the change in kinetic energy of the body on which all these forces are acting. Okay, now today we will start with another set of concepts, and we will start with the definition of something interesting. We will learn to classify forces. Yeah, so today we will begin by understanding the classification of forces as conservative or non-conservative forces on the basis of a property of work done. Okay. So this is work, power and energy, session number 4. So as I said, we will start by understanding classification of forces as conservative or non-conservative forces. So the definition of conservative forces, let us understand that. So we've seen the general definition of work done by a force is F dot ds integration from initial to final position. So it is a path integration. Okay. However, we have seen that in certain cases, the net work done by a force, even though it comes from path integration, it is independent of the path. It depends only on the initial position and the final position. For example, when you look at the work done by a spring force, the final formula that you get after integrating F dot ds only depends on the final position of the spring, that is x final, and the initial position of the spring, that is x initial. That means it is independent of the path that was taken from initial to final and only depends on the final position and the initial position. So when that happens, this type of a force is called a conservative force. Yeah, but we'll discuss about it again, don't worry. Okay. So conservative forces are forces when the work done by a force is path independent. Okay. It is a conservative force. Or another way to define it is that the net work done in a round trip is zero. So what is a round trip? A round trip is a path such that the net displacement is zero. Or in other words, final position equals to the initial position. Okay. So this was the definition of conservative force. Okay. So just make a run through of this once more. Okay, now once we are clear with the definition, one thing we can observe is that any constant force is therefore a conservative force. Not just mg, but any constant force. Okay, because f dot ds integration for a constant force becomes f dot s. And we can see that this quantity f dot s is independent of path. Okay. And f dot s will be equal to 0 when the net displacement is 0 or for a round trip. So anytime we are dealing with a constant force, it is by default a conservative force. So for example, as we discussed last time, weight mg is conservative. It's a conservative force. Okay. Then spring force is also conservative because we've seen that work done by the spring force, this is integration of minus kx dx from initial to final position. So it is given by the formula this. So again we can see that this work done by the spring, it is the solution of the integral finally gives us a formula such that it depends only on final position or state of the spring x final and initial position. Okay. It is path independent. And work done by the spring will be 0 in a round trip, because in the round trip what will happen, x final will be equal to x initial. Okay, so therefore that proves the point that spring force is conservative. Okay, now let us look at an example of something a little bit more more complex. Okay, so suppose we have a situation like this. A particle moves in the xy plane and is acted upon by a force. It's a variable force given by the relation F is equal to, okay, Ritika, I'll take you back to that slide, don't worry. Okay. So this variable force acting on it is given by the relation, let us say, is given by this kind of relation, where F is in newtons and X and Y are position in meters. Okay. So now what is happening is that suppose this is our XY plane and this is the point which is having coordinates 2 comma 1. Coordinates are in meters. Now in one situation we are taking the body from the origin to the point P via this kind of path. This is path 1. And in a second situation, we are taking the body from here to here, but by this path. This is part 2. So this particle moves from the origin to the point P. Okay. Calculate the work done by the force F if it moves by path 1. Similarly, calculate the work done if it moves by path 2 and C. Show that work done will be identical for any possible path. From O to P, and therefore the force is conservative. So we have to show that the force is conservative. Okay, so just take down this question, then I will show you the previous section also once more. Okay, so start working on this question, and I'll also share the previous part. Those who have not finished writing this down, you can, about the spring force being conservative. Okay, now let's discuss about this question, how we will solve it. So, for example, this is the force given to us, and when we are taking it in the first path, let us understand how we will calculate the work done. Okay. So, this is the expression of force given, and this is the path. Okay. So, let's understand the application for the first path. So, for path 1, okay, let us say the path is, let's name this point over here as the point A. So this point will have coordinates 2 comma 0, as you can see. Okay. So the path is OAP. Okay. So the work done in path 1 is the work done from O to A plus the work done from A to P. Okay. Now for work done from O to A, you can see that the force at any general point in between, you have a point like this now. The coordinates are x comma 0. Okay. And at this point, the force is acting like this only. Why the force is acting like this? Because the y coordinate is 0. So it is 2 plus x I cap, okay, at any point which is x comma 0. This point which I'm showing over here. The force is this, and the displacement is along the x-axis only. So when we are at a point like this, whether that point is here or wherever, the force is also along the x-axis, and the displacement vector is also along the x-axis. Okay. So you can see that for this part O to A, the work done, which is f dot ds integration, just becomes 2 plus x dx, integrated from x equal to 0 to x equal to 2. So this integration is very simple. It is 2x plus x square by 2, and on that we have to put the limits x equal to 0 to x equal to 2. So the work done in the part OA is becoming, just put the limits, so that is 6 will become the upper limit, okay, minus 0. So it will be plus 6 joules. Okay. This is the work done in the part OA. Now just make a note of this, and like this we will discuss the work done in the second part, A to P. and that will give us the total work done in path 1, which was the first part we are calculating. Okay, so let us understand the next part. Now, when we are looking at the work done for the next section, okay, which is the point A to the point P. So what is happening in that section, like this is, so going from the point A to P. So A at the coordinates 2 comma 0 and P at the coordinates 2 comma 1. Okay, so when we are at any general point like this over here, the coordinates of a general point will be 2 comma y ranging from 0 to 1. Okay, at this point of time, the displacement of the particle will be along this direction. So my ds vector, okay, so for A to P, when we calculate, the the displacement will be along the y-axis. It will be dy j cap, but the force will have both components. The force will be in some general direction like this, because the general expression of force was this. It was 2 plus x I cap, okay, plus y square j cap. That was the general expression of the force. So you can see that at this kind of a point 2 comma y, the force has an x component which is fixed. It is 4 I cap, and a y component which is variable. This is the force at a general point like this 2 comma y. So whether you are at this point or this point, whatever, everywhere your displacement is like this, but the force is variable like this. So work done from A to P, okay, which is basically integration of f dot ds going from the point A to the point P. That is going to be this thing 4 I cap plus y square j cap dot product with this displacement, that is dy j cap. Okay, going from the point A, which has y equal to 0, to the point P, which has y equal to 1. Okay, so this dot product is very simple. This dot product just becomes y square dy. Okay, so that becomes y cube by 3 from 0 to 1. So that becomes 1 by 3 or 0.33 positive sign joules. So this is the work done from A to P. So now summing this up with the first result, okay, which gave us the work done from O to A. So therefore work done in path 1, this was the sum of these two. Okay, so this is the net work done going from the origin to the point P via path 1. Okay, make a note of this, and now we will see the work done in the second path by a similar method. अरे देखना x कोऑर्डिनेट उसका 2 है ना, so substitute in the expression of force. Okay, so now when you try the same thing for the second path, so let's pick this whole thing up. Okay, just a second. So you should be able to show that the net work done will come out to be the same. Okay, because what will happen is when we calculate the work done for going first along the y-axis, it will again come out to be 0.33 joule. And then when we calculate the work done for going along the x-axis, it will again come out to be 6 joules. Anyhow, let us show that with calculation. So for the second part, what you do is you take this point as B. So this one's coordinates are 1 comma 0. Okay. So work done by path 2, you can see is work done from O to B plus work done from B to P. This thing. Okay. So for work done from O to B, you'll see that the general point is somewhere over here, which has y coordinate variable and x coordinate fixed as 0. So this is a general point 0 comma y. Okay, and y is ranging from 0 to 1. Okay. So at a point 0 comma y, the force is becoming how much? Y square j cap. Okay. This thing, put x as 0 and the differential displacement. So the force is along the y axis now. Okay. And the displacement is also along the y axis. So this is your force and your displacement is also along the y axis. Okay. So for this, the work done f dot ds from O to B, that is becoming this dot product of these two. So that is simply y squared dy going from O, which has y equal to 0, to B, which has y equal to 1. So that is y cubed by 3 from 0 to 1. So as I told you, the path OB will give you the same work done which the path AP had given us earlier because it's along the y-axis. Okay. So this is plus 0.33 joules. Okay. So take down this part and show by a similar method that as you go from B to P, you will again get the work done as 6 joules. So the net work done from O to P via path 2 will again come out to be 6.33 joules. So note down this part and try out the last thing yourself, the work done from B to P if you haven't done that already. So next thing after taking this down, if you haven't calculated already, you calculate the work done for B to P. Okay, so figure out how you'll do all these things. Okay, so let's see what's happening in the path BP. So let us now concentrate on just this part of our second path, going from this point B to this point P. So this had the coordinates 0, comma 1, and the final point P has the coordinates 2, comma 1. Okay. So any point in between here will have the coordinates x, comma 1, where x is ranging from 0 to 2. Okay. So at any point in between x, comma 1, what about the force? The force will be given by 2 plus x I cap plus j cap, because y's value is 1. This will be the value of force, because force in general was 2 plus x I cap plus y square j cap. Now the y coordinate any point is equal to 1. Okay, so because of that, this will become 1 j cap. Whereas the differential, so the force is in some general kind of direction, you can see like this. The force at a point like this is going to have a general direction like this. But the differential displacement, that is going to be along the x-axis. Okay, so it is just dx I cap. So at any point like this is the type of force you have, this is the type of displacement you have. So as you're going along this, at different points, the force will vary, okay, but the displacement will always be along the x-axis. So now your f dot ds, that is the dot product of these two. So that becomes 2 plus x dx. Okay. So the work done, this part, okay, so from B to P, so that becomes integration 2 plus x dx from x equal to 0 to x equal to 2. So that is again the same thing, 2x plus x square by 2. Your limits going from x equal to 0 to x equal to 2. So that is again how much? It is plus 6 joules. So again you can see that the work done for path 2, this was the work done from O to B plus the work done from B to P. So this is this time in this kind of order, but the net work done is the same. Same as we got in path 1. Okay, so make sure you understand this working properly. No, Sarvesh, force is not along x-axis because there is the y coordinate is not zero ना बेटा. तो फोर्स तो वेरिएबल है ना. फोर्स का इक्वेशन देखो ऊपर लिखा हुआ है 2 + x i कैप प्लस y² j कैप. अभी y कोऑर्डिनेट कहाँ जीरो है? y कोऑर्डिनेट 1 है ना. Okay, so hope you've understood this part completely. Now coming to the third part, we want to show that the force is conservative. So that means the general work done is the same for any path. It's path independent, and therefore the force should be conservative. So now going from my origin to that particular point P, which was 2 comma 1. Now supposing I take an arbitrary path. Arbitrary matlab any randomly chosen path. Suppose I take some path like this. And the force acting on the particle while going on this path, at any point of time the force acting is F, and the differential displacement is like this, ds. So the force was given to us by the equation 2 plus x I cap plus y square j cap at any point P x comma y, when the particle is located here at any general point x comma y, the force is like this. Okay, and the differential displacement, now we are taking it as a random quantity, so it has both x component and y component. Okay, so the work done from O to P will be integration of f dot ds from the point O to the point P. So now take the dot product of these two. So when you take the dot product of these two, you can see you will get f's x component, which is 2 plus x, into displacement's x component, which is dx, plus f's y component, which is y square, into displacement's y component, this is dy. Okay, so this whole thing now has to be integrated from the point O, which is 0 comma 0, to the point P, which is 2 comma 1. Okay, so we can break this into two integrals. Integral 2 plus x dx, going from x equal to 0 to x equal to 2, plus integration of y square dy, going from y equal to 0 to y equal to 1. So that will show us that this is always going to be 6.33 joules, irrespective of what path we have taken. So this work done is path independent. So therefore, the force F is conservative. So just make a note of this section now. Okay, so hope this question is fully clear. And through this, the concept of conservative forces in the more general case is clear to you. Okay. Now, next thing we'll look at is the definition of non-conservative forces, which is obvious. It is just the opposite of conservative force. So they are forces which have path-dependent work done. So if the work done by a force is path-dependent, then it is non-conservative in nature. Okay, and work done by a non-conservative force in a round trip will be a non-zero quantity. Okay. So the best example of non-conservative force at this stage is kinetic friction. Okay. So for example, if we are taking a body on a on a rough surface, okay, on a rough horizontal surface, like this, coefficient of friction is mu. Now suppose we are taking a small block. So this is a block of mass m. Now this is being moved from this point A to this point B. Okay, but via two different paths. In one case, we are moving it directly from A to B on the horizontal surface. Okay, and in another case, we are moving it via some more complicated path. Let's say like this. So we can show that the work done by kinetic friction from A to B will be different for the two different paths. Okay, so we'll come back to that. Write down the definition and this thing first, example first. No, it is not constant beta. It changes direction according to the direction of motion. काइनेटिक फ्रिक्शन का मैग्नीट्यूड कभी कभी कांस्टेंट हो सकता है अगर नॉर्मल रिएक्शन कांस्टेंट है, but its direction will keep varying according to the direction of motion or the direction of the instantaneous velocity. Constant force is one which is independent of anything else. Neither its magnitude nor its direction should change. Understood the point, Rahil? So that is what we're going to look at in this particular example also. So here the direction of gravity is like this, going into the plane. Okay, so let us look at this example in more detail next. So if we take the top view, okay, that is we are looking at the horizontal plane from above. So let us say our direct path from the point A to B was this one. Whereas the indirect path that we had drawn earlier, that was, let us say, this path. So in this path, let's say this distance is small a, this distance is small b, and this distance is c. So you can see that c is equal to root of a square plus b square. So if this is path 1 and this one here is path 2. So remember the actual body is moving on the surface like this. So on it there is mg acting downwards, normal reaction acting upwards like this. And if its direction of instantaneous velocity is like this, then there will be kinetic friction acting on it opposite the instantaneous value. So normal reaction will always be equal to mg. So the magnitude of kinetic friction, which is mu n, will always be mu mg. But the direction of kinetic friction varies. So that is why we are seeing that when we go by path 1, the direction of the instantaneous displacement at some point of time is like this. So the direction of kinetic friction will be like this. So for path 1, the work done by friction will become just this much, minus mu mg into c, because you can see here that the differential work done is, so we integrate that from a to b, so that will just give you this quantity. Okay, but for the second path, for path 2, what is happening is when the particle is going in this direction, the kinetic friction acting is like this. Okay, and later when it's going in this direction, the kinetic friction is changed direction and it's become like this. Okay, so it's not a constant force, as you can see, it changes direction. So for part 2, the work done by friction from A to this point, the work done is minus of kinetic friction into small a, and then from here to here, the work done is again minus of kinetic friction into B. So the total work done by friction in the second path is becoming minus mu mg into A plus B. Now you can see that this is not equal to this. These two are not equal. So work done by friction in path 1 is not equal to work done by friction in path 2. So therefore friction is the non-conservative force. The kinetic friction acting here is non-conservative. Okay, so this is a very important example to understand the nature of kinetic friction. At this stage, for us, kinetic friction will be the only physical example of force we'll be discussing, which is non-conservative in nature. The other physical examples like weight, spring force, etc. Later we will see gravitational force, electrostatic force in class 12th, etc. They're all examples of conservative forces. But kinetic friction is the only example of an actual physical force that we'll see, which is non-conservative in nature. Okay, people. So this is the very important aspect of conservative and non-conservative forces. Okay. Now, next thing we move on from conservative and non-conservative forces is the final and most important aspect of work energy theorem, which is the concept of potential energy. Okay. And it's very much linked to conservative force. That's why we have learned about conservative forces first. So we have seen kinetic energy earlier, but now let us understand the concept of potential energy. So what is the definition of potential energy first of all? So potential energy is a type of mechanical energy which is defined for a system. Okay, whenever the system has some energy associated with the state of the system. State का मतलब क्या है? उसका position क्या है? Or the configuration of the system. Okay. So potential energy we generally denote it with the symbol capital U. So potential energy is defined for a system first of all, not for a particle. Okay, so potential energy for a system, okay, is the energy associated with its state. Okay, or a better word for state is configuration. Okay, so this gives us a very easy way to calculate potential energy. Okay, so if the state of a system has to be changed or its configuration has to be changed, then an external agent has to do work, and that work done by the external agent in order to change the configuration is nothing but the change in potential energy. Okay, so when such a system has to undergo a change in its state, okay, or configuration, okay, its potential energy changes. Okay, so that change in potential energy we'll call as delta U. Delta is change and U is potential energy. So its change in potential energy changes such that the work done by the external agent in changing the state of the system equals to the change in its potential energy. Okay, so work done by an external agent in order to change the state equals to its change in potential energy. Okay, so though this is the proper definition of potential energy, but this becomes the working definition of potential energy, because from here we calculate the formula of potential energy by calculating how much is the work done to change the configuration. So we get a formula for delta U, and from the formula of delta U we get the formula for the absolute potential energy U. So we'll take examples of this to understand particular systems, but make a note of this definition first. Potential energy is a state function, so that's why the force we have to consider always has to be a conservative force. So we'll come to that, Sarvesh. Note this down first. So here this work done that we are talking about in the above equation, this only is the W external turn. It is a work done by the external agent in order to only change the state of the system. Okay. There is a change in potential energy. This term only is our delta U. Okay. Now the next point we'll understand here is that if the external agent is doing work to change the state of a system, okay, that means the work done by the external agent must be equal to the work done against the internal force in the system. Okay. For example, if an external agent is doing work to expand a spring, okay, then this work done by the external agent is equal to work done against the spring force, and that is the internal force for the spring. If an external agent is doing work to lift a body by a height from Earth's surface, then the work done by the external agent is the work done against gravity. So gravity in this case is the internal force for the system. Okay. So this work done by the external agent is the work done against the internal force within the system. Okay. So make a note of this point and these examples, then I'll elaborate more about it. Okay, so now the other thing is that since this quantity change in potential energy, okay, now since potential energy itself is the energy associated with state or configuration, therefore delta U, it should be final potential energy minus initial potential energy. Okay, so this final potential energy should depend on the final state only. It should not depend on path. Okay, and this depends on the initial state. Okay, so this shows that delta U should be path independent. Okay, should only depend on final and initial state. Okay. So coming back to what we saw earlier, the work done by the external agent to change the configuration of the system is the negative of work done by the internal forces. Okay, and that is equal to delta U, and this must be path independent. Okay, that means the internal forces must be conservative. Okay, otherwise our delta U cannot be a path independent quantity. So in other words, what we say is that we can define potential energy. Therefore, potential energy can be defined for a system when internal forces are conservative. Okay, and it is defined such that the change in potential energy is nothing but negative of work done by internal conservative forces. Such a term is the work done by internal conservative force. Okay, that is negative of the internal conservative force from initial to final. Okay. And that is a path independent quantity because we are dealing with conservative force. So in this definition, F internal conservative, this is the internal conservative force within the system. Okay. So make a note of this, and then with examples we'll understand this better. Okay, so let us understand this final statement here with two examples. Okay, so basically what we have understood till now, that if an external agent is working on a system such that its configuration is changing. Okay. So in other words, the work done by the external agent is the work done only to change the configuration, the state or configuration of the system. Okay, then the work done by the external agent will equal to negative of work done by the internal conservative force, or that will be equal to delta U. So from this, the proper definition of delta U that we get, it is negative of the work done by internal conservative force, or it is minus F dot ds for the internal conservative force, okay, from initial to final position. Now this quantity will also equal to, this will also equal to the work done by the external agent, provided the external agent is doing work or is working only to change a system's state. Okay, that is, he's not doing any work against any other force, like a non-conservative force, or he's not doing work to change the kinetic energy of the system. He's doing work only to change the state of the system. Okay. So this concept, now let us apply it to a couple of systems and understand this in more detail. So for example, suppose we have the case of the spring mass system. So our system consists of a block on a smooth horizontal surface with a spring attached to it. So the block's mass is m, and the spring has a constant k. Okay, you haven't written down. Okay, finish writing down the upper section, right? Then we'll come back to this. Okay, so let's come back to our example. So we are taking the example of the spring mass system now. Yeah, I'll explain, Sarvesh. Okay. Now let's say here, initially, the spring is in a relaxed state. Okay. So x is equal to 0. Now, next what is happening is that an external agent, okay, pulls the block very slowly. That means as he is pulling it, the velocity of the block is tending to 0. Okay. By applying a gradually increasing force against the spring. Okay. From x equal to 0, that is initially, okay, to some x equal to a finally. So if this is happening, so what is happening is that now we are gradually pulling the block in that direction, and as we are pulling, the block moves very slowly, but also the spring extends. So in order to pull it further, so keep pulling it at a very small velocity tending to 0, we have to keep increasing the amount of external force from point to point so that it always balances our spring force, because this is now become L plus X. So for this system, the internal conservative force is the spring force. So if we take the system, that is the block plus the spring, okay, spring force is the internal conservative force, okay, and this external force that we are applying, this is the external force. In this case, it is acting such that it only does work against the spring force to change the configuration of the system. That is the state of the spring. So this is what is happening over here. So now if you look at the free body diagram, now from this point, suppose the block is making a small displacement dx. Okay. So it is at some x over here. And now the block next changes slightly. So it makes a small displacement from here to here of dx. So during that small displacement, the work done by the external agent, okay, will be equal and opposite to the work done by the spring, because remember its velocity is tending to 0. Okay. So at any intermediate state x equal to x, so x has not yet reached the final value of a, but it has become more than 0. Since the velocity of the block is tending to 0, so its acceleration is tending to 0. So the external force has to be equal and opposite to the spring force. So the magnitude of the external force is Kx. Okay, so just make a note up to here and then we will apply the equation above to find out the formula for change in potential energy. Okay, so here now you can see that the work done by the external agent, which will be equal to F external dx. Now what is the magnitude of F external? It is this. So this term we will plug it in here now. So this becomes Kx dx from x equal to 0, which was the initial state, to x equal to a. So the work done by the external agent is equal to half Ka square. The work done by the spring we can calculate by the formula minus half k into x final square minus x initial square, or it is equal to integration of minus kx dx from initial to final. So whichever way we take, so work done by the spring will be equal to minus half Ka square in this case. So now you can relate these two formula and you can understand that work done by the external agent equals to negative of work done by the internal conservative force, which is nothing but the change in potential energy. Where in this case, this is nothing but work done by the spring. Okay. So the change in potential energy becomes plus half Ka square, going from initial position of 0 to final position of E for the spring. So the three terms in the equation we were discussing, the work done by the external agent when he or she is doing work only to change the state of the system, and the work done by the internal conservative force and the change in potential energy. So how they are related, work done by external agent you can see is equal to negative of work done by the internal conservative force equals to the change in potential energy when the external agent is acting in such a way that it's only changing the state of the system. Okay, so from this we can see that the general formula for potential energy for a spring can be developed. So next thing, general formula for potential energy of a spring. So delta U is negative of work done by internal conservative force. So in this case, it is the spring force. So this work done by internal conservative force is the work done by the spring force, whose formula we've already seen before. So delta U, in the case of the spring, it becomes half K x final square minus x initial square. Okay. So this is basically final potential energy minus initial potential energy for a spring. So by comparison, you can see that potential energy for a spring will simply be defined as half kx square. This is the formula for potential energy of a spring as a function of x, which is nothing but the state or configuration of the spring. Okay, so similarly, we have seen that gravity is a conservative force. Seen that gravitational force is conservative. In fact, at the surface of the earth, weight of a mass m is given by the equation minus mg j cap if we take y-axis as vertical. Okay. So work done by mg becomes this. So that becomes nothing but minus mg delta y, where delta y is the change in the vertical coordinate. So therefore, for a system given by a body of mass m in the Earth's gravitational field, so the system consists of the body present in the Earth's gravitational field. We can define gravitational potential energy. Okay, say with this symbol, such that the change in gravitational potential energy is negative of work done by mg. So delta U gravitational becomes defined as mg delta y. So this in turn means that if the mass m is lifted through height h. Okay. Then delta U will be plus mgh. So in order to lift a mass by a height h, we need to increase the gravitational potential energy by plus mgh. Whereas if the mass m drops through height h, it falls through a height h, then delta U will become minus mgh, because the change in y coordinate will be negative of h. In this case, the change in the y coordinate is positive of h because it is lifted through this height. Whereas in this case, delta y will be minus of h because it is dropping through height h. So the gravitational potential energy changes for a system consisting of the mass of the body and the gravitational field of the earth by a very simple formula given by this. Just make a note of this formula, people. Yeah, so it is independent of path, na beta. So it doesn't matter whether it's moving along an inclined plane or it is directly lifted or it is going by some curved path. It might be going in vertical circular motion. Whatever be the case, it's independent of path. हाँ, but x से मतलब ही नहीं है ना, because work done by gravity डॉट प्रोडक्ट ऑफ डिस्प्लेसमेंट ना. अभी देखो ग्रेविटी का फोर्स कैसे लिखा है हमने, माइनस एम जी जे कैप ना. सो वेयर विल द एक्स कोऑर्डिनेट कम इनटू प्ले. Okay. So these two particular type of systems, we should remember the formula for the potential energy, spring system and gravitational system. So the important formula that we have learned through this today, that potential energy of a spring is given by the formula half kx square, and change in gravitational potential energy for a mass m is mg delta y, where delta y is nothing but the change in the vertical coordinate. It only depends on the vertical coordinate, not on the horizontal coordinate. Okay. So make sure you revise this section very carefully. Now, next time we will be looking at the further application of this concept of potential energy into what is called the general work energy theorem. Earlier we've seen work kinetic energy theorem. Now we will see next time work energy theorem, which is defined for a system. So that theorem will say that work done by any external force plus work done by any non-conservative force equals to the change in kinetic energy plus the change in potential energy for the system. Okay. So this here is work done by external agent, and this is work done by any non-conservative force. Basically friction. There is friction within the system. It will be a non-conservative force. So the sum of these two quantities, that is the net work done on the system, is equal to the change in what we call is mechanical energy. Change in mechanical energy equals to the change in kinetic energy plus change in potential energy. Okay. So that's it for today's session, people. Wish you all the best. Okay. Yeah, I will just take you through the last section again, guys. So make sure you revise this concept of potential energy very carefully, and the relationship between change in potential energy and work done by internal conservative force. So that's it for today's session. Wish you all the best.